This is the basic equation of calculation of butterfly structure. So this is the basic equations, and we can calculate the our output from this. So you can factor I is representing input and BCD is representing the repeat output, and x0 x1 x2 are representing the output. Okay. So this is the basic output of our butterfly structure, where I representing the input and W representing the repeat factor. So this is the basic RTL of butterfly unit, or R4 point FTS structure that we are using. Here, this is the basic RTL structure, where you can say that it containing the 4 butterflies and a bit reverse here. So here you can say that 4 butterflies here and a bit reverse unit here. We can, so first we bit reverse it, and we increase 4 butterflies. We calculate the 8 or which is outputs which we are identify. So what the operation that we require to perform these 4 point display structure? First one, what we have to do is to bit reverse. Okay, so for bit reversal case, what we are doing is here you can see that we are reversing our bits from 0 0 0 0. It's okay. 0 1, when we reverse it, it becomes 2. When we reverse it, then 0, it becomes 1, and then 1, it becomes 2. So we are actually reversing our bits so that it become in place of the algorithm. Here input signal is placed in bit reverse order at the start, so that we do not require extra memory to perform effective results to in-place algorithm. Okay, so this is the first unit that we perform is bit reverse, and next is array export post multiplier. So what we are using is the for the multiplication we are using radix 4 post multiplier. That is the very efficient multiplier and efficiency. You can see here that higher radix multiplier leads to more than 1 bit multiplication at each cycle. Okay, so implementation of radix 4 post multiplier required to generate -1 bit, -2 bit, -b and 2 bit. These are the basic products in it that needs to be generated, and we have reached the multiplication, all of which are computed using shift operation and complementation. Okay, so this paper consider radix 4 boost multiplier, which makes collection of 3 bits and name each collection xi. Dependent on xi, we compute the partial product and shift it by 28 number of bits and add them together. As each partial product is being shifted for 2 places, number of partial products are reduced by half. So radix 4 boost multiplier is actually used to reduce the partial product by half. Okay, so this is very efficient post multiplier. And in the case of adder, what we are using is we are using ripple carry adder and Covestone adder, both at a time. Okay, so ripple carry adder is very efficient in the terms of area. Okay, so limitation in terms of text it propagate, but it has a more delay. Okay, so we have less area and more delay. And Covestone adder is very efficient in terms of area, but it's in terms of delay, but it is very inefficient in terms of area. It contains the highest area but least delay. This is the basic nature of Covestone adder, and this is the basic nature of ripple carry adder, that it is a least area and highest delay. So as carry bit is ripple in the full in the adder, it is called ripple. As carry bit ripple into the next full adder, it is called as a ripple carry adder. So parallel fixed form of carrying adder is known as Covestone adder. It engages the largest area corresponding to other parallel fixed adder because of the maximum number of carry, generate and propagate signal. The propagation delay depends on the number of intermediate stages in the adder. For each intermediate stage, carry propagate and carry generate signal are generated concurrently. Okay, so carry generation is only log n, that is known as fastest adder, is mainly used in the electronics industry for designing a fast arithmetic circuit. So it has lower fan out at each stage, therefore consumes lower delay. 32-bit Covestone adder is same. Here it is the picture of 32-bit Covestone adder, and as I said, you can use the highest area and least delay. So this is the basic property of Covestone adder. So I have compared that, and I have designed the particular 4.2 FFT structure using Covestone adder and ripple carry adder and fuse multiplier. So I have compared the result also. So as you can see here, that I have designed that 4.2 FFT structure with the Covestone adder here, you can say, and with the ripple carry adder, and the Verilog code has been successfully simulated and synthesized on Canon size design with the 14.7, and design works well for 24-bit input and output, 4 input with real imaginary part taken into consideration, and